This is Mr. Kanyile for Masterclass VirtualX session. Still going on with our calculus, especially graphs. Once we finish graphs, we'll go on to the interpretation of calculus. Remember, when you differentiate a cubic graph, you get a parabola. For example, if I have a graph like this one, if I differentiate that graph, I will definitely get a parabola. I'm just making a rough example. Remember, when you differentiate this, it will be a parabola. If I differentiate a parabola, it will be a straight line. Remember, this is to the power 3, so it will be 3 minus 1 to be 2. This is to the power 2. Now, remember that this part, the stationary points, are very important. If in the original graph, these are the stationary points, they become the x-intercept in the derivative. That becomes very important. And this point here, which is the point of inflection, the concavity of the graph, it will become the turning point of this one. If we master that, we'll never go wrong in these sessions. Remember, we said this graph here, in the original graph, the stationary points, the one point is here, the x value, the other x value is there. And the point of inflection, it will be the turning point in the derivative. That becomes crucial for us to be able to understand this. What is it that we are given here? We are given the derivative, not the original graph, but the gradient. This is the gradient or the derivative of the cubic function. So at times we might be given this graph, which is the derivative of the cubic function, but you'll be asked questions on this graph which is not given. This is the case with this problem. It was set in November 2010. We said we must touch on this because the examiners have not asked this question in a long time. Now, this is what we have here. We have the derivative. At the back of our minds, we know that this value here, which is this value, originally it was the x here was that x there, and this x there was this x here. So if I'm given this value, I can tell what was the original values of the x of the turning point. The x of the turning point of this value is minus 2 and 6. I can see that from this derivative, which is the gradient. Now, this is what we're given. We're given the derivative of the original graph, which we don't have, which is the cubic function. We're also given this one, which is the straight line graph, where it's called to mx plus c. This is c. What is c? C is nothing else but the y-intercept, the point where this graph will be cutting the y-axis. This is the graph of h. We said this is g prime, therefore this is h. Now I can see what is the y-intercept in that graph. I can see this point here is called the y-intercept. So this graph must cut these are the y-axis, these are the x-axis. This graph must cut the y-axis at minus 4. So this position here, it is minus 4. I got it from the given equation of h. Now, I'm also given the gradient here. There are certain things that I can find from the gradient. Remember, we're dealing with calculus. Calculus is nothing else but the study of gradient. Wherever there's gradient, we study that in this particular section. Remember, what is the gradient? Gradient is nothing else. Gradient, it's the change in y over change in x, over change in x. This is what gradient is. Dy over dx. This is what gradient is. Even when you do calculus, we say dy over dx. We're just looking for gradient when you differentiate. So when you differentiate this, we get this one. So what is actually this is? This is the gradient of this one. We call it the gradient. Why do we call that the gradient? Look here. Let me just explain that quickly. Do you see the gradient of this graph this side? The gradient of this graph this side is positive. After the gradient was positive, it became 0 here. Okay. After the gradient was positive, then it became 0. dy dx, dy dx is 0 at this point, at the stationary points. After it was 0, it becomes what now? This side, you can see that the gradient, our gradient is negative. After it being negative, it went back in being 0. Our gradient here is 0. There is no slope here. Then eventually it was back to positive. goes back to positive. Our gradient is positive this side. This is what we see. So when we call this the gradient of this one, we understand it in that context. If this is the gradient, watch here. The gradient started being what? With being positive. So this part is positive. This graph is positive above, it is negative below, it is 0 here. So this graph started being positive. After being positive, it went into being 0 at this point. Thereafter, it becomes what? All this part is negative. All this part is negative because it is below the x-axis. After being negative, it becomes what? It became 0 at this point. Then it becomes positive again. So it is actually the gradient of that one. Hence, those two will be those two which are the x values of the stationary points. Right. So anything that has to do with gradient we start with. Remember, what is the gradient? A gradient is the distance traveled along the y over distance traveled in x-axis. This will give us a slope. Change in y over change in x. This is what gives us the slope. If in y, x, I'll get a different slope. That is a slope. It is determined by the change in y over change in x. That's what gives us a gradient. Now I can tell the gradient of this one because I know it's 2. This is actually 2 over 1 because a gradient is a ratio, something over something, changing distance traveled in y over distance traveled in x. So if I ngihambe 2 times ka y ka x file ngihambe kangaki once for me to get that gradient of 2. If ka y ngihambe 2 times ukuze ngithole 2 ka x file ngihamba 1, so that I'll get the gradient. This is how they got that gradient. If ngihambe ka 4 ka x file ngihambe kangaki ka y ka x file ngihambe ka 2 ukuze ngithole the same 2 over 1. So in this case, my gradient is 2. This becomes important. It forms part of our calculus, the gradient, the study of change. Now watch here. I know this distance. I remember distance is always positive. So from here to here, I've moved how many times? I've moved 4 times. So my gradient. Ka y ngihambe 4 times. Ukuze kuthole i-answer ewu-2 because my gradient is 2. How many times must I move along the x-axis? I must move 2 times. What is this telling me? If I've moved 4 times here, to get on this, if I've moved 4 times, to get on the same line, I must move a certain units as well. So ngimuveka 4 la, how many times must I use along the x-axis? I must move 2 times to get on the same line. So I know the value of x here, it is 2, by understanding the fact of the gradient. So in this case, I already know the x-intercept and I already know the y-intercept by just understanding what the gradient is. It is nothing else but the distance traveled in y over distance traveled in x. That gives me the idea of the points that I have in my graph. Now, the first question, write down the coordinates of E. What are the coordinates? You bring both x and y. And where is E? E is at this point. On this line, what is the value of x? The value of x here is not, there's no x in here. The value of x will be 0. So if I'm asking you the coordinates of E, we already know that there's no x here. X is 0. What is y here? Y is minus 4. These are the coordinates of E. Where did I get this minus 4? I got it from the straight line graph because E is part of the straight line graph. So this will be the C of the straight line graph as well as the C of the parabola, because this is the same point for both the straight line and the derivative of the cubic graph or the parabola in this particular case. So this C belongs here, the same C belongs on the parabola. So I know that value there. Now when this next question says determine the equation of G prime, which one is G prime? It's this one. In the form of y is equal to ax squared plus bx plus c. We already know c because c is nothing else but the y-intercept in this particular case. So the value of c here will be minus 4. I'll be short of b and a. Finding the equations. You'll find these questions all over. Questions that talks about finding the equation. Whether it is the straight line graph, this will form part of our functions. If I have these graphs, let me look at this graph. Y is equal to mx plus c. Number 2. y is equals to ax squared plus bx plus c. Number 3, let me just quickly take the third one. Let me take the hyperbola. Y is equals to a over x minus p plus q. Let me just make example of this. Determine the equation, find the equation. I'm addressing the question that says find the equation. In any graphs it works the same way. Find the equation, find the equation. Definitely you'll find it there in graphs. You might find it in trigonometry graphs. You might find it in paper 1 functions, as we find it here in calculus. So whenever there are graphs, you'll find questions that says find the equation. So you must know those general equations. This equation says y is equal to mx plus c. Why do we study this in calculus? Because there's gradient, and calculus is the study of gradient. What is it that we're looking for when the question says find the equation of a straight line? We are just looking for m and c. That becomes important. Number 2, when I'm giving this parabola, like in this case, what is it that we're looking for in the question that says find the parabola? You're just looking for a, b, and c. I'm saying you're just looking for a, b, and c when you're given a parabola and required to find it. Let's work in reverse. Let's turn that backwards. I'm saying to you, when you're looking for the equation of a straight line, you're looking for m and c. When you're looking for the equation of a parabola, you're looking for a, b, and c. Let's work that in reverse. What is it that you are not looking for when you're looking for a straight line? You're not supposed to look for y and x. Let's come back to this one. What is it that you are not supposed to look for? You are not supposed to look for y and x. You look for any other thing there except y and x. That's exactly what you do when you're looking for the equation of any graph. You don't touch y, you don't touch x. You find any other variable that is there. In this particular case, we're not going to touch y and x. We're looking for everything that is there. In this case, it is m and c. Here, you don't touch y, you don't touch x. So you're looking for a, b, and c. Let's come to this one, the hyperbola. What is it that you'll be looking for when the question says find the equation of this hyperbola? You're not going to touch y, you're not going to touch x, therefore you're looking for a, p, and q. That's what you do. Hence, in this particular question, the question says find the equation of g prime, which is this one, in this form, which is this form. And we know exactly what we have to look for. We'll have to look for A, for B, and C. We've already spoken about C. But remember what C is. It is nothing else but the y-cut, the y-intercept of this graph, which is this one, which is 4. Why do we use this 4 there? It is the same point. It is the same point where this graph and this graph cuts. Hence, they share the same point. Why? They share the same y-intercept. In this particular case, it is -4. So we know the value of C there, which is -4. And let's look at this graph. We're looking for the equation. Remember, this graph can come out in 3 ways. This is A. It can come out in this form, number B. It can come out in this form, y is equals to a into x minus p all squared plus q. It can come out in number C in this way, which is y is equals to a into x minus x1, x minus x2. It is the same thing, it's the parabola, All this means one and the same thing. This is the cube, the parabola quadratic function, same thing, parabola. So it can come up, it has 3 equations. This one has got 2. There's another one for this one, which is y minus y1 is equal to m into x minus x1. It can come out, the straight line can come out in that way as well. Remember, you mostly use this one when you are given gradient and any other point. Now, let's look at this one. When do we use this one? We use this one when we are given a turning point. If in this case we knew the coordinates of the turning point, it would have been easier for us to use this one in that particular form. Remember, these two, P and Q are the coordinates of the turning point, where X is P and Y is Q. Right, we use this graph when we are given a turning point. Then when do we use this one? We use this one when we are given these 2 here. These are the roots, or the X-intercepts. This is the first one, the second one. This is the X-intercept. When we are given this, we are going to use this one, where these 2 are the X-intercepts. then you'll be able to find, given the x-intercept and any other point, you'll be able to use that one. Now let's look when do we use this one? When we're given any 3 points. This one is no longer examinable to find it given 3 points, but mainly we'll be given these two. This one we use when you're given a turning point where P and Q are the coordinates of the turning point. This one you will be using it when we're given the x-intercepts or the roots, where this is the first x-intercept and the second one, and any other points for both of them. Now what are we given here? Are we given option the first one or the second one? Oh, I can see that we are given the x-intercept. I know this value, x-intercept, I know that value, hence we're likely to use that one. And we know at the back of our minds the value of this value here, it should be -4. If it is not -4, then I will know that I'm wrong. In this case, we're given the x-intercept and another point. What other point that we know in this graph? We don't know this one, we only know x here, we don't know y, but here we know both x and y, which is point E, which we calculated in the first one. Remember now we want to determine the equation of g prime, not of g, of this one. Fortunately it's g prime in the form y is equal to ax squared plus bx plus c. We know that c will be -4. What is it that we are given here? We are given the roots, the x-intercepts, and this point. Hence we'll be using this equation. X-intercept first, the second x-intercept, then we'll be able to solve the graph using the other point to have one unknown. Let's write the equation that we have to use. We set the equation that we are going to use because we are given the x-intercept, the roots, this becomes important, and this point. We're going to use the equation y is equals to a into x minus x1 into x minus x2. There are things that we know. We want it in this form, so we know that this value here must be equals to -4. So we're short of b and a. What is it that we know about a? We know that our a must be positive because our graph is facing upwards. If our graph was facing downwards, this a was going to be negative. In this case, we know that this value here is a positive value, which will be put in there. Let's put what we have. At the moment we have y is equals to a into x minus. What is the first x-intercept? Let's write it, it is -2. Hence it will be minus times minus, it will be +2. Be careful of that. Into x minus. What is the second x-intercept? It is 6. We push it in there. Still, we can't find the equation in that form. We've just substituted the x-intercept, the roots. This is -2 and 6 in this particular case. Let's look at the point that we have in this graph. Is there a point that we have in this graph? Yes, there's a point that we have, which is point E in this particular case. What are the coordinates of point E? There they are. It is 0 and -4. These coordinates become crucial. If we got them wrong there, we're likely to get them wrong in here as well. Let's do this thing. Let's substitute that. This is the x coordinate, and this is the y coordinate. Where there is x, we'll push in 0. Where there is y, we'll push in -4, so that we can have one unknown. In this particular case, this will be unknown, then we find it. Let's do this thing. Wherever there is y, we push in -4 is equals to a into, what is x? It is 0 plus 2 into, what is y? Y is, I'm still x, 0 minus 6, so this is x, right. Why were we doing this? We were trying to have only one unknown, in this case, which is a. Once we find a, you are going to substitute in there and break these brackets so that it is in the form that the examiner wants it. Let's do this thing. So this is -4 is equals to, let's work this thing out. This is 2, bracket means times, this is -6. What is 2 times -6? It is -12 times a, it will be -12a. Remember, we're looking for a, we will divide by -12 on both sides, -12 on both sides. Therefore a, that goes with that, we're left with a equals to negative divided by negative, it is positive. 4 into 4 goes once, 4 into 12, 4, 8, 12 goes 3 times. This is the value of a. A in this particular case is 1 over 3. Did I expect to get a positive value of A? Yes, I expected to get a positive value of A because the graph is concave up. If it was concave down, this value of A was going to be negative. So we're on the right track. Now, but the question did not say find the value of A. The question says find the equation of ax squared plus bx plus C, this parabola in that form. But we know the value of A. Now you take, this step becomes very important. I love this step. It becomes very important. Let's work on this step. I'm going to have y is equals to, what is my A in this particular case? It is 1 over 3 into A, this is 1 over 3. Let me break this. What is x times x? It is x squared. Look at this 2, it's minus 6, bigger number, so it will be minus 4. The difference between that is minus 4. Then 2 times that, it is minus 12. That's what we have. Remember, I'm looking for it in this form, and this value of C must be minus 4. I keep that at the back of my heart, my mind. Now let's write this equation. This times that, this is y is equals to 1 over 3 x squared. This times that, it will be minus. So 1 times 4, it is 4 over 3x. 1 over 3 times 12, this will be minus 3 into 12, 3, 6, 9, 12 goes 4 times. This is the equation in that form. This is A, this is B, and this is C, and C is in fact minus 4. So we are correct. So we've responded to this question, determine the equation of G in the form. This question just was testing us the understanding of functions, in particular the parabola, and what we are given. We are given it in that form, so we employ that equation where we put x1 as the first root and x2 as the second root, and find any other point that was given in this graph, in this particular case, which is this one. Let's move on to the third question. Write down the x coordinates. Your language becomes important. Here, write down the x coordinate, singular, plural. Many things, one thing. Write down the x coordinates of the turning points of G. Remember, we're not given G, we're given G prime. But they ask us about the graph that is not even there, that we can't even see. But from the explanation that I did here, I said this point here, this x coordinate, it's this one, and this x coordinate is that one. So they're just asking us whether we understand this part of calculus, which is nothing else but the gradient. And it does not say calculate, it does not say think, it simply says write down. It's just checking whether you can recall what you've learned in your classes. Let's write them down as the question requires. Write down the first x coordinate. The first x will be equals to what? The first x will be equals to minus 2, and the second x will be equals to. These are the turning points in the original graph, not in G prime, but in G. These were the turning points. These were the turning points. So the other one, the other x is equal to 6. So it is important that we must understand those facts. The last question here that I want us to look at, it says write down the x coordinate of the point of inflection. Point of inflection is the concavity of the two graphs. Where these two graphs, this one is concaving up, this one is concaving down. How do you find the x-intercept here? You find this becomes the first derivative, then the second derivative we'll be using it to find the point of inflection. This is the parabola that we have. I've got to find, if I differentiate this and make it equal to 0, I'll be able to find x. But let me find an easier way to do that. If I have coordinates here, x and y, x and y. If I'm looking for this x, I will take this x, add it to this x, and divide by 2. Do I know those x that are there? In this particular case, the first x was minus 2, the one that is here. The other x was 6, maybe the one that is here. So if I'm looking for another way of finding the point of inflection, you simply say x1 plus x2 over 2. This will give me another x of the point of inflection. What is the first x that we have there in this particular case? It is minus 2. The second x will be plus 6. This is all over 2. Even if you find the second derivative, you'll find the same solution. Let's work it out. This 6 minus 2, it will be 4 over 2. Therefore, x there will be equals to 2. Remember that we've already found this x. We've already found this x when I was explaining the gradient. Right? So what is this saying to me? The point of inflection becomes the turning point in this one. The x of the turning point in this particular case, which is c. We've already found it. So in other words, there were about 3 different ways of finding that one. I could have used this one because we're told, this was important, that AB is parallel to the y-axis. This is parallel to this one. So this distance is the same everywhere in this part. So from here to here it's 2 units. From here to here it's 2 units. From here to here it's 2 units. So the value of x here at the point of inflection of the original graph, it is equals to 2. We can find it in this way. You can find it in this way as well, where you said this x plus this x will give us also the point of inflection. So that's about the graphs that you'll be required to respond on calculus. Remember, graphs have got marks. Make sure that you understand it. Once you understand one graph, you'll be able to understand all the other graphs. But practice for you to be perfect. Thank you.